Welcome everybody to Algebra 2 Section 5.4, Graphing Polynomial Functions and Finding Root/Zeros. So a polynomial function is a function of the form following, and this has a lot of math jargon in it and is thus very confusing. Essentially what you need to know is all the a's that we see here are coefficients. And all the x's you see here are, well, x's to certain powers. And what we see is we see some power n, that's our highest power, and then n minus 1. So for example, if this was like x to the 5th, this would be x to the 4th, and then minus 2 would be x to the 3rd. And then we see anywhere here, this could be middle terms if there are more, and then going down to x squared, x to the 1st, and no x. And so if there were more terms in here, they would fit right there, and this would be higher, such as 6 or 8 or you name it. That's essentially what we need to know for this as far as a polynomial term. You'll notice there's no variables in denominators, just like we covered when we talked about polynomials. There's no variables in denominators there either. And all coefficients are real numbers, so no non-real numbers, none of the complex numbers as we talked about them. And all exponents are whole numbers, or sorry, no complex numbers that are non-real, I should clarify, because real numbers are also complex. And then all exponents are whole numbers, so non-negative numbers, no decimals, no fractions, no zeros for exponents. Sorry, that includes 0 for exponents, but no negatives or decimals or fractions. And the degree of a polynomial function is the value of the greatest exponent, which we've covered before as well. So let's talk about 6 different polynomial parent functions, and you could have further ones. So constant is a degree of 0. So the parent function of this is f of x equals some constant number c. This would be like y equals a number. And so for example, if you had like y equals 3, for example, you'd go up to 1, 2, 3, draw your horizontal line there, and that'd be a constant function. Linear is a degree of 1, and that's f of x is equal to, the parent function I should say, is f of x is equal to x. And that's a y equals mx plus b with a slope of 1 and a y-intercept of 0. Quadratic is a degree of 2, so f of x equals x squared, and it follows this u shape that we call a parabola. Cubic is a degree of 3, so f of x equals x cubed, which follows this general shape, passing through the origin as well. You'll notice all of these do, except for the constant function not necessarily passing through the origin. Quartic has a degree of 4, and this is f of x equals x to the 4th. And you'll notice the parent function actually looks identical to the parent function for the quadratic, but not all quartic functions look identical to quadratics. And quintic has a degree of 5, so f of x equals x to the 5th is the parent function. And similarly, you'll notice that this looks a lot like the cubic one for parent functions because those are identical. But once again, only the cubic and quintic parent functions are identical. No other cubic and quintic functions are truly identical. So let's talk about turning points. Turning points are the point at which a polynomial function changes direction. So for example, it'd be this and that, those 2 points on that graph, where it goes from left to right, up, 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 and then turns to go down, 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 down. And it goes from down, down, down to up, 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 up. They're also thought of as the highest and lowest points, which is what we're going to talk about right here with these bullets. So if the turning point is higher than any nearby point, which is the case here, it is called a relative maximum. Now, this point right here in orange now is the relative maximum, which you might want to label. I will abbreviate. Let me see if I can make that arrow less bad. That's better. And that is not a true maximum because it goes up forever and has no maximum because of that, but it is what we call a relative maximum, as in between the extreme ends of the graph, anywhere between those orange slashes, that's our highest point. It's the highest point of any around. Think hilltops. And then conversely, if the point's lower than any nearby point, which we see in this green one down here, that is called a relative minimum. Because it may not be a true minimum, which it isn't on this one, it has a no lowest point, but it is the lowest point between those two extremes. Think valleys, the bottom of a valley. So I'll label that one as well, relative minimum. And the maximum and minimum values are called extrema, or more extreme portions of the graph. Now, not unbounded extreme, aka going to either positive or negative infinity, increasing or decreasing without bound, we call it sometimes. And turning points define where a function is increasing or decreasing. So from left to right, it's increasing here, decreasing on this interval, and then increasing on this interval, going back to previous units when we talked about increasing and decreasing intervals. Now let's look at how to find these using a graphing utility, aka graphing calculator, such as our TI-84s, Calc84 on the iPads, or Desmo's graphing calculator online. So you graph a function, so you enter the function into y equals, so such as y equals x cubed minus 6x squared plus 7x plus 2. Remember, f of x and y are the same thing, so I could just as easily write y equals all of this instead of f of x equals all of that. And then from there, you go to the calc menu, which is found using the second button and going to trace. And then you select whichever value you want to find. So if it's maximum you want to find, then you select maximum. If you want to find relative minimums, then you select minimum. And then from there, it asks you for a left bound, a right bound, and it asks you to guess, which you don't need to if you set good boundaries. And so if you have questions on how to find those, I would encourage you to come and find me in the classroom sometime so I can show you that. It's not really something I can show well on the video, unfortunately, because Calc84 on the iPad just doesn't do it the same way as the TI-84s. It actually does it a lot easier with a lot less work. But essentially, you just move your cursor to the left of the value you want to find and hit enter for left bound. Move it to the right of the value you want to find, hit enter, and your value should be between the left bound and right bound. It'll make two dashed lines on your calculator that are perfectly vertical. Then you hit enter through that. When it asks you to guess, you can just hit enter again, and it spits out the value to you. And the same is true for finding zeros/roots. You just hit the option 0 in the calc menu instead of maximum or minimum values. So in order to find the relative minimums and relative maximums/maximums, minimums/minimums, and the increase and decreasing intervals of this, we'll graph this function, which I already have plugged into Calc84. So I'll go to y equals. We see it's plugged in currently into this second function, where y1 of x. And so I have the first one toggled off because that's not what I'm doing. And I'm going to go ahead and graph it. And we see this graph. If your graph looks a little bit different for some reason, or it's more stretched out perhaps, or collapsed, you can always hit zoom and go to zoom standard. Select that, and it'll turn it into this again. And the tool we want to use, we want to tap on tools, and we want to find extrema, which we just said relative maximums and minimums are called extrema. And it instantly tells us those are the 2 points. Now, we don't have to write out that entire decimal, and actually that entire decimal is even rounded at that point after 5 digits. We'll make it a general rule that we'll round to the hundredths place, which is 2 decimal places. So for a relative maximum, let's record it here, would be 0.71, 4.30. And our relative minimum would be 3.29, negative 4.30. And we only had one relative maximum, one relative minimum, because there's only one hill and one valley. If it were to happen to have more hills and more valleys, which some of these graphs will that we'll see, then we'd have multiple of either minimums or maximums, or potentially both. Now looking at our increasing and decreasing intervals from left to right, it increases from the bottom left of the graph up to our first hilltop, the maximum, and then it decreases from left to right between our maximum and the minimum, our hilltop and our valley, and then from the valley, the minimum, relative minimum, it increases to the right for the rest of the graph. And reminder that we talk about these increasing, decreasing intervals as far as whether the y values are increasing or decreasing, and the interval is the x values on which they increase or decrease. And we always use parentheses, not brackets, when we define our intervals, because it cannot increase or decrease at a certain point, but rather only between points. So increasing interval would be from negative infinity, comma 0.71, which once again defined that first portion of the graph. So this portion I'll highlight in blue. And then it decreases in a portion I'll highlight in green right here, which was between 0.71 or 0.71. I shouldn't put the parenthesis on the second end yet. Comma 3.29, which was the x value of the minimum. And then it increased again, which will make light blue on this last portion forever. And so we would put a comma here saying there's a second increasing interval, so it's intervals, plural. And that is 3.29 all the way to infinity. And then that covers the entire graph, so we only list one decreasing interval because there's only one area from left to right that it decreases on. So now we're going to go ahead and work on graphing these polynomials and plotting them on our graphs as well, like our actual physical graphs, not just our graphing calculators. And we're not going to use a table. I think that's rather silly, actually, to use tables for these kind of functions. Instead, we will be doing it by finding the relative minimums and maximums and finding any roots or zeros and using those to help us graph. And we'll be writing down those points, relative minimums, maximums. We don't have a space here to write zeros and roots because we're going to be working on finding that in a later portion of this section. So we'll just start with finding relative minimums and maximums and progressing from there. And then we'll identify domain range, the increasing and decreasing intervals, and end behavior, like we have in the past. So graphing this first one. I also have that one preloaded into Calc84. However, I can only preload 2 of them because I have the free version. Maybe I should upgrade to the paid version at some point so I can get some more. It's asking me to rate it. No, thank you. I don't want to take the time, to be honest. Yeah, I'd get 10 different functions, 0 through 9. But I toggled it on and off to do my next function. Oh, they're both the same. Silly me. I guess I didn't have it preloaded after all like I thought I did. So anyway, let me just type this in now. So I have x to the third, get out the exponent, minus 3x squared, minus 3. Now I can graph this and move, and I will show the extrema to be 0, negative 3, and 2, negative 7. So relative maximum, 0, negative 3, and relative minimum, 2, negative 7. So I'll go ahead and graph those. And I also need to note the end behavior for this, that it went down from here, down to there, and up from here. And boom, I have my graph. Now, I should note that these are actually a little more curvy than I made them out to be. And our actual graph reflects that. So now our increasing, decreasing intervals, domain and range, and end behavior can be found. So the domain is how far left and right this goes. It goes left forever and right forever, and you'll notice a consistent theme on polynomial functions that the domain is just all real numbers, which is double-lined R, or you could do the negative infinity, infinity. The range here is how low to high it goes, all the y values, and that's down forever, up forever with no breaks or gaps in between, which is also all real numbers, or negative infinity, infinity with parentheses on each. The increasing interval, 2 of them from here to here and there to there. And so the first one would be negative infinity over to 0. And the next one would be from 2 to infinity. Once again, using these x values. And the decreasing interval, which we'll do in green, would be between the two. So between 0 and 2. And now our end behavior. So as x goes to negative infinity, as x goes to the left forever, which is this way, the y's are going down forever. It's going down and left. So that's negative infinity. F of x, remember, is just y. And so now as x is going forever right, the right portion of the graph, the y values are going up. And so it's going up and right forever, positive infinity for the y values. Moving on to number 2 here. I'm going to go ahead and plug in this to my graphing calculator as the app wants to load again, and then give me an ad. Maybe I really should get the paid version at this point, but alas, I'm too cheap. All right, it's all typed in, so I'm going to graph, move it so I can actually find it. I messed something up here. My graph doesn't look correct. So let me look at this again. Oh, that should be a minus x to the 4x to the fourth, or 4x to the second, excuse me. And yes, that little mistake can change so much. Now this looks more like a W. Not a perfect W by any means, of course. And so now as I look at my extrema, I notice I have 2 relative minimums, or 2 valleys, and 1 relative maximum. So I record where these are, rounding to the nearest tenth, or nearest hundredth, excuse me, or 2 decimal places. So relative maximum, just one of them at 0,5, which I'll go and plot. Relative minimum, minimums, which are negative 1.84, comma negative 3.31. And then as well as 1.09, comma 2.95. And so I'll go ahead and plot those as well. And those obviously aren't perfectly on any lattice points or grid points here. So I have to just kind of estimate where those would be. And that's okay, because we're just doing a rough sketch of this graph anyway. And I know we connect it, go up forever, connect it and go up forever, and it'll look something like that. And once again, I'm not going for a perfect sketch here. Our sketches will get a little bit more precise as we introduce roots and zeros later in this section. Domain and range. So domain again will be all real numbers, or negative infinity to positive infinity. Range, however, it does have a lowest point, and it's right there, the true minimum, which shows us that it's going, that you can either say y is greater or equal to, greater than or equal to, that lowest is that, and it goes up forever. The y value of negative 3.31, the y value of our true minimum. You could also write it as negative 3.31 with a bracket, comma infinity going up forever with a parenthesis. Then we can have our increasing intervals, which would be these two. And so that would be from negative 1.84 in the x value to the x value of 0, as well as the x value of 1.09 to infinity. And then the decreasing intervals in blue would be from negative infinity to negative 1.84. As well as negative 1.84 to 1.09. And the end behavior, both are going to positive infinity as it goes to the left and to the right forever. So infinity and infinity. Let me clarify, these are both positive infinity there. Moving on to example 3 here. We're going to go ahead and plug this in to our graphing calculator as well. we have negative x to the third minus, or excuse me, plus 3x squared. And this is our graph, and I'm going to go ahead and zoom standard. There we go. And I'm going to look for my extrema again, my maxes and mins. And I see them here as 2, 4 for my relative maximum and 0, 0 for my relative minimum. So I'll go ahead and jot that down. And so I'll plot those points. And I know it followed this pattern. So from there I can see that my domain and range is forever negative, forever positive for the x values, as it is every time. So that's the double line R for all real numbers, or negative infinity, comma infinity. For the range, it's also forever down, forever up, so all the y values are included. And so that'll be all real numbers as well, or the negative infinity to positive infinity again. The increasing intervals are between the two extrema. That's actually the only increasing interval. So that's between 0 and 2 for x values. The decreasing intervals are from the left to the relative minimum and the relative maximum all the way to the right. So that's negative infinity, comma 0, as well as 2, comma infinity. The end behavior is x goes forever to the left, the y goes forever up to positive infinity, and as x goes forever to the right, y goes forever down to negative infinity. Moving on to number 4 here, so I'll type this into the graphing calculator. And once I go again to zoom standard, getting to see what goes on here. Look for my extrema. I have 2 relative maximums as well as a relative minimum. So I'll go ahead and jot that down again, rounding the nearest hundredth, 2 decimal places. So relative maximums are at negative 1.57, comma 6.50. Let me rewrite that 0.50. As well as 1.16, comma negative 1.91. And the relative minimum is at 0.41, comma negative 2.59. And so I'll go ahead and estimate the plot of these. Once again, it's just an estimation, so it doesn't have to be precise by any means. And so it'll look something like this. And then from there, I can establish my domain and range. Domain is once again all real numbers, so it will be every time, or the negative infinity to positive infinity. And the range, it goes down forever, and it goes up to that y value at the maximum, which is 6.5. So that is negative infinity, comma 6.5. The bracket for 6.5 or 6.50. Forgot to mention the other way to write that would be y is less than or equal to 6.5 or 6.50. The increasing intervals would be from forever left to the relative maximum, and then between the relative minimum and to the right to the next relative maximum. So that would be negative infinity to negative 1.57, as well as from 0.41, comma 1.16. And then the relative minimum, or excuse me, the decreasing intervals would be right there in the purple, the first relative maximum to the relative minimum, and then from the second relative maximum down to forever to the right. So that'd be negative 1.57, comma 0.41, as well as 1.16, comma infinity. And then end behavior here, as x goes to the right and the left, both the y values for both of those go forever down to negative infinity. On the number 5, I'm going to go ahead and graph this. And as I graph, I'll once again go to Zoom Standard just to get a better look at it. And I look at my extrema, and I'll go ahead and note those down, rounding to the nearest hundredth again. So relative maximum is negative 0.12. Comma 0.06. The relative minimum is 1.45, comma negative 3.76. And once again, I'll go and sketch those, not needing to be perfect. And knowing it looks something like this. Domain is, as always, all real numbers, or the negative infinity to positive infinity. And the range is also all real numbers, forever down, forever up, as well as the negative infinity to infinity. Increasing intervals are in green, so that would be from negative infinity to our relative maximum, negative 0.12, as well as from a relative minimum to positive infinity, so 1.45, comma infinity. And then our relative minimum is, or some decreasing intervals between our relative maximum and minimum, so negative 0.12, comma 1.45. And then last but not least, the end behavior here would be as x goes to negative infinity, y goes to negative infinity. And as x goes to positive infinity, forever right, y goes forever up to positive infinity as well. Now we're going to work on finding end behavior patterns. So there's patterns for this. So we can use your graphing calculator to determine the end behavior of the following functions. But rather, given that we just determined end behavior of a number of functions, I'm just going to go ahead and write these down here. And then feel free to go and verify them using your calculator, or pause, find them using your calculator, and then verify them with what I say in the video. So for number 1 here, as x approaches both negative and positive infinity, forever left and forever right, the y values are going to positive infinity, forever up either way. The same thing is true on number 5. And then on numbers 2 and 6, they're both going to negative infinity regardless. From this, we can surmise some information down in this table before I even finish numbers 3 and 4. However, I will go and finish 3 and 4. Then on 3 and 4, when they have an odd degree, or just exponent on a variable, this went to negative infinity and infinity, and this was the exact opposite. So we notice when the highest degree is even, that they're either both positive infinity or they're both negative infinity. And the difference between whether they're positive or negative infinity actually has to do with the leading coefficient, the first number, or the number with the that is being multiplied with the variable that has the highest coefficient, highest exponent, excuse me. So positive, positive, both positive for end behavior, negative leading coefficient, negative leading coefficient, negatives for both of our infinities. And so that would go right down here, where when the degree is even and the leading coefficient is positive, and behavior will look something like this. As it goes from left to right, they'll both go up for the y values. And negative, as it goes left and right, they both go down. Think a parabola and an upside down parabola. Given the nature of what a negative out in front for the leading coefficient does of reflecting it. Whereas for the odd degree, when the leading coefficient is positive, like on number 3 up above, you have forever down on the left and forever up on the right. So looking something like this. Whereas when they have the negative leading coefficient, it just flips it. So even degrees either both go up or both go down, and odd degrees go one of each. And between positive and negatives, it just reflects or flips the direction of each end behavior. So now, without even graphing these, we can identify the end behavior of the following functions for numbers 7 through 14 purely by noting the degree and the leading coefficient. So on number 7, the degree, the highest exponent is 1, and the leading coefficient is a negative. So the end behavior is thus going to be, I should clarify that the degree is 1, but more importantly, we note that it's odd. And so the end behavior is this box down here. Forever positive on the left, forever negative on the right. On number 8 here, the highest degree is even, power of 2. The leading coefficient is positive 12. And so they both go up, forever left and forever right, both go forever up. On number 9, the highest degree is again 3, or is again odd because it's 3 this time. And the leading coefficient is again negative, so to go forever up on the left, forever down on the right. Continuing, number 10 here, the highest degree is even, 4. And the leading coefficient is negative, so they both go down. And we can continue to fill out this table. 11, highest degree is odd, 5. The leading coefficient is positive, so to go forever down on the left, forever up on the right. Example 12, highest degree is even, exponent 4, positive exponent, both going up, or positive coefficient, leading coefficient. On number 13, the highest degree is odd, 7, and the leading coefficient is negative, and so it'll go forever up on the left, forever down on the right. And on 14, highest exponent is 2, which is even. Leading coefficient is negative, so it'll go forever down, both left and right. And this tells you immediately what's happening at the ends of the graph. It doesn't tell you anything that's happening between the two, so it could look like that, or it could look like this, or it could look like this. Lots of different possibilities there, but we do know what's happening at the ends of the graph. So based upon the graphs we see on 15 and 16, we can determine the sign of the leading coefficient, whether it's positive or negative, and whether the degree of the function is even or odd. So on 15 here, because they're both down, that means it's even, and it's also a negative leading coefficient. If they go the same direction, it's even. And so because these go different directions, it's automatically an odd degree. And because it goes negative, positive, or down forever, and down then up, it is a positive leading coefficient. Number 17 through 20 here, we're told what the end behavior is, and now we're supposed to tell which of the following functions, check them, that match that. And so what I'm going to do here is draw the arrows for this. So forever left is forever down, so that's a down arrow. Forever right is forever down, that's also a down arrow. So this fits any even degree function that has a negative leading coefficient. So that matches the description of this third box as well as this last box. Next up on number 18, as x goes forever left, it goes forever down for the y values. And as x goes forever right, it goes forever up to positive infinity for the y values. So that tells me it's an odd function immediately, so I can rule out the first and the second to last options. But now I need to note whether the leading coefficient is positive or negative, and it is in fact positive since it goes down then up rather than up then down. So I'm looking for a positive leading coefficient where the degree is odd. So that's the second option. The third option are the 2. On number 19, it goes up and then down from left to right. So it's again odd because it's switching from up to down or down to up. And this time when it goes up to down, that means the leading coefficient is negative. So we're looking for something with a negative leading coefficient and an odd degree. So that'd be the first one and the fourth one and the last one. On number 20, both y values go up forever for end behavior. And so we're looking for one that is an even degree with a leading coefficient that's positive. So that'd be the second option and the fourth option. And this fifth option. Next, we're going to focus on finding zeros. So zeros, which you've talked about before, are the same thing as roots or x-intercepts or solutions, and it's the points at which the function intersects the x-axis. A polynomial function of degree n, so whatever the degree is, can have at most n real zeros. Real means, obviously not the non-imaginary or the non-lateral numbers. And an even degree polynomial will always have an even number of real zeros, or potentially no zeros with 0 zeros, and 0 is an even number. An odd degree polynomial has an odd number of zeros, such as 1, 3, or 5. So on number 1, because this is an odd degree for the highest exponent, that means that it's automatically going to have either 1 or 3 zeros, because it can have at most the degree, so it can have at most 3 different real zeros, and it can have either 1 or 3 because it has to be odd. So we can graph this to determine that. And so we can go ahead and go to our handy dandy graphing calculator and start typing this in. Go to Zoom Standard again. What I like to do, you don't have to change it every time on Calculate on the TI-84s. It just kind of stays with the same window you have it set to ahead of time, unless you change it manually, something else. And now in the tools, I'm going to hit the root button, because remember, zeros are the same thing as roots. Or on your TI-84, as I mentioned earlier, you'd go to second calc, which is the same button as trace at the top. You'd go to 0, and then you would use your left boundary, right boundary again of wherever the x-intercepts or zeros or roots are to locate just 1 0 between your left bound and right bound that you make. So I'm going to go ahead and hit the root button, and I find they're at the x values of -2, 0, and 1. So you could write your answers a couple different ways, just like we learned before. So you could write x equals -2, 0, 1, a list. You could write 3 separate answers, x equals -2, x equals 0, x equals 1. That'd be fine too. You could also write ordered pairs, -2, 0, 0, 0, and 1, 0. Because they're x-intercepts, the y value must be 0. I'm typically going to write the blue one because it's the least amount of writing, and I'm very lazy. It's also just what makes the most sense to me to see the information presented. And so we can go ahead and graph these 3 x-intercepts though. And it can also be helpful for us to note where some of our extrema were to help graph this. If I click that, I can see extrema we're at negative 1.21 approximately, and comma 2.11, as well as the other x and y value for the relative minimum. And so I'm just going to go ahead and plot those where they approximately are. Once again, not looking to be perfect here by any stretch of the imagination. And then going to just connect these accordingly. So just those 5 points really help us graph this. Any relative minimum or maximum, the extrema, as well as any zeros we have, roots, x-intercepts, whatever we want to call it. We'll do the same thing on number 2 here. And we see this weird M looking thing. There is already zoom standard. So I'll go and look at the roots, and I see there's 4 roots. We could have known that it would have been at most 4 because the highest degree was 4. The degree was 4, the highest exponent. And then it was either going to be 0, 2, or 4 because it had to be an even number since it's an even degree. And here it happens to be 4, negative 2, negative 1, 1, and 2. So I'm going to go and write x equals negative 2, negative 1, 1, and 2. And I'm going to go and graph it. And it's helpful to find those extrema as well as we're going to go ahead and look to graph. And so I'm going to take note of where those are. I don't necessarily need to write the information. I can if I'd like, though. And reconnect. And there we have it. Also want to note that linear factors of a polynomial reveal its zeros. So you can factor something and then find its zeros. So for example, here you could factor this. I'll show this off to the side. You would factor out a GCF here. So it would be x squared minus 2x minus 15. And that would be equal to your f of x, so to speak, or your 0. You could say 0 equals all that. And then you could factor this further by making an x, and negative 15 at the top, negative 2 at the bottom, and negative 5 and positive 3 do the trick. And we can use the shortcut because it's a 1x squared. So it would be x minus 5, and x plus 3. And that would be our, quote, factored form. F of x equal to x times x minus 5 times x plus 3. And if we solve each of these, so setting them each equal to 0, which would happen if 0 equaled all of that. If the y value was 0, then it's an x-intercept. And we end up getting, as I'm going to actually move this up here, x equals 0, x minus 5 equals 0, x plus 3 equals 0, each of those factors, which gives us x equals 0 is just the answer, x equals 5, and x equals negative 3 as we solve for x. And I like writing them from least to greatest, so that's what I'll do. So they can be found either algebraically or graphically by doing the math of the equation or by actually just graphing it. And then we have a little flow chart, not a flow chart, excuse me, a graphic organizer here. And we have one for both, as I rotate this, an odd degree and an even degree. So if we wanted to go ahead and graph this, we can using a graphing calculator. So this is x to the third plus 6x squared plus 8x. Okay, and I'm going to go and do zoom standard just in case. Nope, it's already there. Cool, that's nice. So I'm going to look for the roots and the extrema, and I'm going to go ahead and take note of those. So the extrema are going to go in for the turning points here on this graphic organizer, and I'm going to label them as relative minimums and maximums. and I'm going to round to the nearest hundredth again, as I have been before. So go to turning points. So negative 3.15, comma 3.08. And as mentioned, that is the relative maximum. And then you can have negative 0.85, comma negative 3.08. And that is the relative minimum. And I'm going to go ahead and graph those. And then now I'm going to go ahead and check again where those zeros were and write that down as negative 4, negative 2, and 0. And so I'm going to put that down here. And plot those. And now I can connect this. Oh, I plotted one of the relative minimums wrong. Oopsie. That's better. And by one of the relative minimums, I guess I just meant the relative minimum since there's only one. And so now I can find all the rest of this information for increasing intervals, decreasing intervals, domain and range. I could have found the end behavior and the parent function right away. I'll go ahead and do that now since I guess I should have done that earlier, or could have done that earlier. So f of x equals x cubed is a parent function, the most basic version of this with no transformations. And then behavior, because it's an odd function with a positive leading coefficient, is always going to be as x approaches negative infinity, f of x goes to, or the y goes to negative infinity, and as x goes to positive infinity, f of x or y goes to positive infinity as well. Now let's talk about increasing, decreasing intervals. Increases from here between the forever left to the relative maximum, and then from the relative minimum forever right. So that'll be negative infinity, comma negative 3.15, as well as negative 0.85, comma infinity. And the decreasing intervals is between the relative maximum and relative minimum, so negative 3.15, comma negative 0.085, or just negative 0.85. And now for domain and range. The domain here is, as always, all real numbers, which can be rewritten as negative infinity to infinity. And the range is also forever down, forever up, all real numbers again, which is also negative infinity to positive infinity. And that can put a nice little synthesis of all the information we've been finding on one graph here on one page. And so once again, like I said, we'll have another one here for an even degree, here a degree of 4, highest exponent of 4. All right, so I'm going to go and plug this into my graphing calculator as well and do the exact same thing. Nice little add there. All right, and that's our graph. So I'm going to go and look for the roots and the extrema. I'm going to go and take note of each of these, starting with the turning points for extrema / relative maximum, relative minimum. So there's 2 relative maximums, and that's negative 1, 0, as well as 1.37, negative 4.85. And those are, once again, the relative maximums. And then our relative minimum is at negative 0.37, 0.35. And so I'm going to go ahead and sketch where these are on the graph. Oh, my apologies. I changed these up as far as which one's a relative minimum and relative maximum, so let me fix that. There we go. The first two are the relative minimums, and the last one was a relative maximum. Oh, whoopsie. I did it at 0.48 instead of negative 4.8. And then the zeros. So I see my zeros are at -1, 0, and 2. So I'll go ahead and jot that down. And graph that. And one of my relative minimums was a 0, so that took care of graphing that one. And there's our graph, which we could have known the end behavior already in the parent function, given that it's slid back to the previous one somehow, given that it was a quartic, or a degree of 4. So the parent function is f of x equals x to the 4th, and the end behavior is that as x approaches negative infinity, or forever left, y approaches positive infinity, or f of x approaches positive infinity, and as x approaches positive infinity, f of x again approaches positive infinity. The increasing and decreasing intervals are between that minimum maximum there, and then between that minimum all the way to the far right of the graph. So I'm going to go and write that down. That'd be from -1 to -0.37, as well as 1.37 to infinity. And the decreasing intervals are forever left to the first relative minimum, and then from a relative maximum to your true minimum of the graph. So it would be from negative infinity. Let me rewrite my infinity there. Didn't like that, I guess. Comma -1, as well as -0.37, comma 1.37. And the domain and range. The domain is all real numbers, or the negative infinity to positive infinity. And this time the range is not all real numbers because it does have a lowest point. So one way you could write it is that y is greater than or equal to the true minimum, which is the y value of -4.85. Or you could also rewrite this as -4.85, comma infinity, with -4.85 getting a bracket. And that would be the end of Algebra 2, section 5.4.